Hello, my name is Florian Atteneder. I'm a PhD student in Jena, and I'm talking to you today about boson stars, and we're also collaborating here with people from Técnico. So, first things first, what are boson stars? I think in some talks we have heard a bit about them, but not so much, but for the sake of time, I'm keeping this brief. So, in short, boson stars are soliton-like solutions of Einstein-Klein-Gordon equations of motions. Those equations of motions you can derive when you minimally couple a complex scalar field to an Einstein-Hilbert term. And the first to consider such a setup was Kopp in 1968. And if you want to know more about evolution techniques and also single star models, I refer you to this review. For the sake of this talk, I'm restricting myself only to so-called mini boson stars. Those are those stars for which the potential is that of a free scalar field. And I've also put here the mass to 1, which is convenient for our coding. And then so I also have here the why in the title, why bother and try boson stars. Well, I mean, should I say more at the Dark Matter conference? Well, essentially, if we want to have a chance on detecting something that's basically invisible to the electromagnetic spectrum, our best bet is probably to look at gravitational waves. But for that, we need to aid our experimentalist friends and provide them with gravitational wave templates. And that's the main goal of our project. Okay, so let's switch gears and talk about initial data. This is the scalar field amplitude, how it looks like for head-on collisions that we are trying to do at the moment. And so I'm going to have a quick discussion about what's the problem with initial data. So usually if one wants to want to simulate a head-on collision, you know usually how a single isolated star looks like. But for a head-on, you kind of have to break this assumption of a star being isolated and put those two isolated models onto the same grid. The question is, how do you do this? There's a big question mark here because there is no straightforward way and no clear way to combine isolated star models. But the Einstein field equations give us at least some guidelines on how we can do that, actually on how we should do that if we really want to study gravity, general relativity, and not some other theory. And so these are these equations, and I thank Tim very much for elaborating, emphasizing this before. But if you take a look at the boson star literature, what has done to this day is that most of the people have kind of ignored these constraint equations for a moment and instead just put their plus sign, meaning you just really linearly combine your isolated star models and take that as an approximate solutions to your constraint equations and then go from there. Then there has been recent improvement on this superposition because this kind of approximation of initial data can in some cases lead to very weird artificial collapses which are not to be expected. But what we really should do is that we look at constraint solved data, which Hannes just had a nice talk on. So, and that is a tough problem. One has to solve those equations here numerically. And with this situation present in the current literature, and we in Jena trying to do now head-on boson star simulations in general, we asked ourselves, well, if we want to do something, will it even matter which kind of superposition, which kind of way of initial data construction we use for the final result of an evolution? For example, will there be distinguishable differences in the final gravitational wave signal? So that's the project we're currently working on. Unfortunately, I can't yet give you a fair comparison. So I'm only showing you kind of part of a result we have obtained so far, and it is a stable and convergent evolution of a head-on collision. And the setup we're considering here is an equal mass boson star head-on collision. So this is now the improved version of the superposition data I'm trying to evolve here. And for the experts here, we're using the BAMS code, which is developed in Jena and uses a generalized harmonic formulation for the evolutionary part. What's interesting here on the right is the kind of two analysis variables of our initial data. The top half shows us the logarithm of the sum of all the constraint equations we have in our systems. We have to ideally solve exactly, but we can't because it's, well, numerics. But we see we have here regions where we are kind of deviating a bit more from those constraints, meaning we are kind of a little away from true GR, but overall this looks fairly good if you look at the scale. And the bottom plot is really just the Ricci scalar indicating, well, there are two centers with high curvature, and those are supposedly the centers of the stars. Okay, and if you put this on the computer and let it run, you get a gravitational wave signal that looks something like this. Notice the time scale here. This is pretty long. This is 27,000 amps. And about the anatomy of this signal, so we have here an initial big spike, and this is really when the two stars first touch each other and collide. But then notice that there is also a long tail of non-negligible residual signal, which is fairly not to be expected for black holes, black hole head-on or a neutron star head-on. So this is boson stars in that regard are very characteristic, have a very characteristic gravitational wave signature, if they exist, of course. But I want to demonstrate to you that we can do this in a convergent manner. So how do we? I give you now a very non-rigorous way to demonstrate this. So we just zoom into here part of the signal and look at different resolutions where we have obtained the result. We can see, well, for different resolutions we have some differences here and there. But if you watch now closely, I will gonna swap out the two lower resolutions and bring in two higher ones. You will see that the differences go away. So we can see something's changed. And now we can play also the same game if we focus on the late part of the signal, where we can see we have accumulated quite some phase differences over time between the different resolutions. But again, if I swap the slide, I see, well, there appears to be something convergent. And that's a very nice result for us. And with that said, I want to thank you for your attention.
Questions?
By the way, I also have a video. What would be an art talk without the video? Gotta admit, it's a boring one.
You now have a perfect talk because you have both a convergence test and a video, which I think is a perfect numerical relativity talk.
Thanks.
So yeah, this is really nice what you're trying to do. So just to be clear, you are trying to solve the constraints, but you're relying on the helper trick of superposition to try and give you something that's sort of equilibrium in the same way as Hannes was doing for the neutron star with the dark matter. Is that right?
Kind of, almost. I think from the helper trick, you really just exchange the delta part that you subtract, and you only really modify that. But for the scalar field part, where you have the scalar amplitudes, it's a superposition in either way, so there's no difference between whatever Palenzuela did before and Helfer for the scalar part. But you're right, we then just take the scalar part from the superposition and then adjust the metric part to be constraint satisfying.
Okay, thank you.
Any other question? Quick question?
At the beginning, you said that you couldn't give a fair comparison. Can you just tell us now what is the unfair comparison that you can already say?
Well, weren't you at the last meeting, David? No. So the thing is that the thing is that so if you set up the elliptic solver, there are different formulations you can apply to find your constraint satisfying data. And the one that's currently implemented is that tries to solve for an ansatz that is conformally flat. But when you look at the superposition of the Helfer trick here, that's just a naive addition, and in that way you can't get something that's asymptotically flat. Conformally flat. So in that regard, it's really not the same.
Okay, so I think we can thank our speaker and move to the next one.